So my name is Tempel. I'm the CTO at VoxelSensors, and my presentation is probably on the other end of the spectrum than the previous presentation on light fields. So our focus is really to build a 3D sensing system with low bandwidth requirements and also low computer requirements. And I'm going to present to you today how we achieve that. So first, VoxelSensors is a startup company. We started about 4 years ago, almost 5 years ago, actually, in March 2020. We were about 20 people in the team. We're VC funded. We're still developing our first product, which will come out to the market end of next year. You will learn more about it in the presentation. VC funded for that development. And we developed a new type of sensor called a single photon active event sensor, which we use for spatial sensing among other modalities like eye tracking. So today's presentation is about the spatial sensing side. And I'm first going to introduce this new sensing technology that we developed. So that's our proprietary silicon to achieve low latency, low power spatial sensing. So what is this single photon active event sensor? So it's a multimodal sensor, and the primary function of this sensor is the detection of sparse optical signals. Sparse optical signals being spots in the scene, scanning laser beams, fiducials, any sparse optical signal that can be picked up by silicon in the right bandwidth, wavelength, I mean. And we try to do that, the picking up of the detection of the sparse optical signal with a minimum amount of optical energy. So we want to use as low photons as possible in order to make confirm the detection. And we want to do that in a very short amount of time. And so we developed sensors which will localize in the image plane detections in both time and space. Sensors will give pixel coordinates of the presence of the sparse optical signal, and it will give a timestamp when this signal was detected. And our sensors are based on SPADs. So the second modality that we provide with our sensors is reading out this SPAD imager, these bit planes that are generated in the imager. I will go in more detail in the next slides. So what is our purpose, primary purpose? This is a simulation of a moving spot, a scanning spot. It generates an active photon flux. When you image the scene with an optical lens, you generate this optical flux profile on the sensor. And added to that, there is ambient light, or maybe other sensors, flood illuminator, etc., which are also generating photons in your wavelength range. And so if you start looking at this flux profile with a SPAD imager, you end up with a very noisy image because the sensors are very sensitive. So the SPADs, which are single photon sensitive, they will trigger to every photon which is present, which is projected on the sensor, and you get a very, very noisy SPAD image. So what we developed is a SPAD imager, which includes spatial temporal filtering inside the image plane. And the spatial temporal filtering is going to distinguish between the active photons, which are related to the sparse optical signal that we want to measure, and are going to distinguish these active photons from ambient photons, which follow traditional Poisson distributions. This is happening for every pixel inside the image plane with a minimum amount of power. And then after the spatial temporal filtering, we have further event-based filtering, which will reconstruct the presence or location, the presence of the optical signal in the scene. And so at the output of the imager, after this on silicon filtering chain, is a stream of data X, Y, T. So X, Y, the positions in the image plane, and the T is the timestamp of the detected sparse optical signal. In this example, I give one dot, but of course the sensor is capable of tracking multiple dots in the image plane. So what's nice about this sensor is that we are going to use that for spatial sensing. The both modalities which are offered by the sensor, the XYT stream and the SPAD imaging mode, they can be very useful for the spatial imaging. And I'm going to zoom in into how we use the XYT stream, so the location stream, timestamp location stream to construct 3D information. The sensing principle is very simple, actually. What we do is we are going to scan with a laser beam, a high-frequency laser beam scanner. typically based on MEMS technology, which can be very miniaturized. We are going to scan a single laser dot on the scene in this Lissajou pattern, for example. These scan rates can be up to tens of kilohertz, for example, 20 kilohertz on the fast axis, and the slow axis you can choose, of course. This scanning laser beam is used then in conjunction with a single photon active event sensor. And we're going to use the data from each of these components to reconstruct the depth. From the projector, we query the projection vector at each timestamp of detection. And from the receiver, which is the sensor, we gather the detected locations X, Y, T. And for each timestamp T, we can reconstruct with the projection ray and the detected location in the image plane, we can reconstruct the 3D position. And so creating a stream of world coordinates, X, Y, Z, T, which will then build up the 3D point cloud. The compute required for this is very, very small, since the stereo matching is done in the time domain. So you have almost instantaneous matching of the two stereo pairs, and the triangulation is a very simple mathematical step. So from a compute point of view, this is a very light process because we are fully serializing the point cloud construction. How does that look in reality? So this is a demo that we currently have with our proof of concept silicon that we developed. So on the top side, you see a stereo pair of sensors in this case. Each of the sensors is detecting the flying dot, which is flying around in the scene. And so per timestamp, we are triangulating each dot sequentially. And you see here this moving hand, which is generated by the triangulation method. What is nice is that each measurement that you do, it almost has suffers almost no motion artifacts, because each measurement is almost independent. Every 40 nanoseconds, for example, a sampling rate of 40 nanoseconds of the sensor, every 40 nanoseconds, a new 3D point is created, which is almost independently from what was generated before. So motion artifacts on this 3D data are almost non-existent, which is very nice for highly dynamic situations. There are a lot of benefits which are connected to this type of sensing system. First of all, we are able to sense with very low optical power, mainly because of two things. First one is we are concentrating all available optical power in a single dot at a time, which means that fighting ambient light fluxes like sunlight becomes much easier. And secondly, the SPADs are single photon sensitive, so we can use very low active light energies to make a 3D detection. Secondly, the density of acquisition is very flexible. Firstly, we can generate high densities because the SPAD-based detection is very fast. The sampling rate up to 25 megasamples per second of the sensors normally supports definitely something like 20 kilohertz of scan rates, which means 40 lines can be thrown on the field of view every millisecond, which generates decent densities. And moreover, because the acquisition is completely serialized, we can choose the kind of density that we want to have. For example, we can throw dots on the scene in certain parts of the scene, while in certain region of interest, we apply a denser sampling of the scene. So the adaptiveness of this serialized sensing technology can be used to adapt with respect to what is happening in the scene. From a robustness point of view, we can design these active event sensor systems for 100 klux ambient light, even above, and that is due to the in-pixel filtering, the spatial temporal filtering that can be tuned to distinguish even in high ambient light conditions between the active photon flux and the ambient photon flux. Moreover, in terms of robustness, the laser beam scanning method offers increased robustness in situations, for example, such as mist or in dusty environments, which are typically present, for example, in industrial environments or outdoor industrial environments. And also the laser beam scanning method, where we are sampling a very sparse optical signal for each of the systems, ensures that there is a very low chance of crosstalk between different sensing systems looking at the scene simultaneously. And then lastly, we can make the system very low power because of the sensing method on the one side, but also on the compute side, the sensing method offers state-of-the-art power consumption. This is a summary of the merit table, where I try to summarize the different requirements in a number of domains. You can recognize actually two blocks which I highlighted in blue. And from my point of view, there are two big groups. One group is really focused on the robustness with respect to an environment: darkness, sunlight, dust, snow, particles, concurrent systems which are looking at the same scene, but also a requirement on deterministic depth. So that means that it is not based on machine learning, which can be, is very hard sometimes to qualify in terms of functional safety. And then the second aspect, or the second domain, is oriented around low latency, low power consumption, and small footprint. And with our technology, we can address both of these very strict requirements in terms of 3D sensing. And I picked out one line here, the drones, which is surprisingly a very demanding domain, both in terms of size, latency, power consumption, but also in terms of robustness, because these drones go into a variety of environments. And there we are working as VoxelSensors as part of a consortium which is being supported by the European Commission in a project called SPEAR, where we are researching spatial perception and embodied autonomy research. And this project allows us to investigate the usefulness of our sensing technology in the context of these drones, and to confirm the validity of our proposition of laser beam scanning triangulation in the context of drones, addressing a wide variety of difficult requirements. Today, where we are, we have evaluation kits available based on our proof of concept silicon. Two of them are available today. This Andromeda 1, which are discrete cameras and a laser beam projector. Andromeda 2 is an integrated stereo pair of sensors with a discrete laser beam projector. Both evaluation kits come with an SDK and our support, and they output streaming point clouds, as I explained earlier, XYZT, and also standard depth maps similar to your current 3D sensing devices. Andromeda 3 is a miniaturized SDK, which is more oriented towards mobile or more demanding applications where you have a requirement for small form factor, and this will be available beginning of next year. In terms of sensor roadmap, as I said, today we have evaluation kits based on our proof of concept silicon. We are currently developing our first product, which will come out Q3 2025. And if you're interested to explore what this sensing technology could mean for your application, feel free to reach out to me or to anybody else in the VoxelSensors team. Thank you.
Okay, thank you, Ward. I have a question. What are the potential uses for this technology in different industries long term?
It's a difficult question to answer because it can be very, very broad. In terms of applicability of this 3D sensing method, I think there's a wide range of applicability. For example, the triangulation method can offer very high accuracy in fields like metrology, where in the implementation that we have, because we are sensing a sparse optical signal, so one dot at a time, the addition of multiple viewpoints in order to increase your accuracy is quite trivial. The compute complexity just scales with the number of viewpoints, which is very different from other sensing technology. So in metrology, I see a very nice future. Also in terms of AMR and drones, where low latency, for example, obstacle detection is required with deterministic depth methods, so not inference-based. This technology can offer solutions when it comes to being very robust against environmental conditions and aggressive systems.
Okay, and maybe you can expand a bit on what are the key advantages of your technology versus similar technologies?
Whew, do you have a couple of hours? Do you have a specific technology in mind to compare against? Because the field of 3D sensing is very wide.
No, just what you would see as your main competitors, maybe.
As I said, those two domains. One focus on low power. VoxelSensors' primary focus at this moment is on wearables and smart glasses, where footprint but also power consumption is a very strict requirement. I think from what I've seen, VoxelSensors offers a system which will offer state-of-the-art power consumption when it comes to active 3D sensing. And then the other domain is robustness. Because of the laser beam scanning method and the active event sensors paired together, the robustness aspect will definitely be a big selling point for this technology. So those are the two unique selling points, and we can compare against very different methods. For example, the light field technology from before, which is a very nice technology, but requires quite some compute and bandwidth, and we've heard it also in the presentation. If you have that available, it's a nice technology. Technologies like indirect time of flight, which were popular a few years ago in mobile and are still there today in industry, are also very nice technologies, but come with limitations in terms of accuracy and robustness against ambient light, etc. So depending on your requirements, there is a set of 3D technologies that you can choose from. But when your requirements include robustness and power consumption, I think this is definitely, VoxelSensors technology is definitely should be in your list of choice.
Okay, thank you much for now.